Hello everyone, and welcome to Microtrac's free webinar, 3D Image Analysis, Know Your Materials. My name is Claudia Gaitan and I will be your moderator today. If you have any questions during the presentation, please type them in the question box in the control panel, and we will be happy to answer your questions at the end of the presentation. A recorded version of this webinar will be available on the website microtrac.com. Your speaker today is Terry Stauffer. Terry works closely with Microtrac as a particle characterization specialist, and he has over 40 years of experience in the industry. In today's presentation, we'll cover the ability to isolate different particulate components in one sample by first identifying them and then quantifying them. Then we'll review 3D image analysis technology and go over its important advantages over 2D technology. We'll go over 3 examples of component isolation in real-time applications: reflective glass beads, aggregates for construction, and metal powder laser melting manufacture, which is a 3D printing process. And lastly, we'll be wrapping things up with a brief summary. We'll also be answering your questions and going over how you can request a complimentary lab analysis of your sample. In many applications, there's a need to identify and quantify different particulate components in one sample. This can be easily accomplished with patented 3D image analysis and the use of the search query and filter classification features in the software. 2 different types of subcomponents in samples can be identified. The first is contaminants from various sources, like from the process itself or from handling and packaging later. Various size and shape parameters can distinguish contaminants from the main product characteristics. The second is particulates, which lie outside particular control specifications for the product manufactured, like particle which might lie outside the aspect ratio, surface roughness, or sphericity, or even transparency limits for those products. Here's a schematic which shows the simplicity of dynamic image analysis as used in the PartAn 3D analyzer. The dry sample placed in the funnel on the right moves on a vibratory feeder to the edge of the sensing zone, where it falls by gravity through the sensing zone and is collected in the sample box at the bottom. A light strobe on one side of the sensing zone lights the particles as the digital camera on the other side photographs the particles as they tumble through the sensing zone. A video file of the analysis is stored, and distributions and summary data for upwards of 30 morphological parameters, which include sizes, shapes, and transparencies, for each particle are calculated and reported. The 3D mode works by having the camera track the tumbling and rotating orientations of each particle. From those multiple individual images, it identifies and calculates the maximum and minimum parameters so that all 3 main axes, which are length, width, and thickness, are quantified. This patented feature makes it the only image analyzer which provides 3-dimensional data. This is an open instrument photo of the analyzer. The sample analysis technology could hardly be more simple or robust. This is the set of parameters Microtrac reports for its PartAn dynamic image analysis product line. Rather than go into each in any detail, I'll describe in 4 general terms what they measure. First, of course, is size. We give you 18 different size measurements of each particle in various diameters, lengths, widths, thicknesses, and more. The last 3 columns are shapes of different natures and are generally expressed in ratios of size parameters. Form factors include 13 different parameters that indicate how closely the particle is to being a perfect sphere, or various aspect ratios or elongations of that particle. Surface roughness parameters are just that. 3 different parameters can indicate the roughness factor of the particle surface. 2 other parameters report the overall light intensity coming through the particle and the curvature of the particle as a gradient of light intensity. Don't be overwhelmed. No more than a few parameters are needed for any particular application, but there are enough choices here to meet your particular needs. Here are some of the software features available for component identification and quantification. In the View Particles display, one can view the entire image file and sort on any parameter. A search query can be set up so that there are also searches for particles with defined characteristics. A scatter diagram can also be used to compare particles relevant to 2 different morphological characteristics. The XY graph and table can display the relative percentage of each of the different components in the sample. And now I'll turn it over to Terry.
This View Particles display is a workhorse of the software for method development. A camera frame view is shown in the upper left, and a video file view in the lower left. This video file view can be scrolled through all 84,000 particles that were measured in this sample. This file can be sorted on any parameter and the value of the parameter for each image displayed. It can also be exported to a spreadsheet listing the value of all 36 parameters for each particle. The fused or agglomerated particle in the upper left of the frame has been selected in the blue box, and all of its size and shape parameters are displayed in the list in the upper right. The Search Particles button, Callout 1 on the left, opens a particle query window shown below the parameter list on the right. This versatile window is used to create searches for different types of components in the sample which match the selection criteria entered in the window. The simple example shown is to select for all particles with a length greater than 25 microns. If this query is selected, the image file will change to display only those particle images in the sample which are greater than a length of 25 microns. The next slide will go into more detail for the powerful particle query capability. And following that, we'll get into the scatter diagram display, which is a further tool for analysis and method development, and can be selected from this display under the Search Particles button above, Callout 2. Here's a larger view of 2 of the important method development tools in View Particles display. First is the Particle Query window, Callout 1, where any number of parameters per search and number of different searches can be set up and used later whenever desired. They can also be modified and reevaluated. When added, all searches show up in the second window, Callout 2, which is shown here highlighting the one currently selected, at which time the image file contains only those images included in the search, and the scatter diagram, to be discussed next, shows only the distributions for the particles selected in the search chosen. The highlighted search above for 3D images greater than a length of 150 microns and a transparency greater than 0.5 shows statistics that the particles included in that class make up about 79% of the sample by volume and about 36,000 of the 84,000 particles by count or number in the total sample. This is the scatter diagram tool, which can be opened in the View Particles display just covered. It always displays the distributions of any of the parameters which represents the distribution or subdistribution selected in view particles. This is the scatter diagram view for the entire sample distribution we've just been using as an example. First, I'll highlight the capability of this display. The scatter diagram itself is the diagram in the lower left, where the blue dots indicate the location of each particle in the sample with respect to the top red x-axis graph and the right side red y-axis graph. The darker the blue area in the scatter diagram, the more dense the population of particles there. Any of the 36 parameters can be chosen, see callout 1, to be plotted on either graph. In this display, F, or ferrite length, is plotted on the X graph and transparency in the Y graph. Transparency is on a scale of 0 to 1, where 1 is perfectly transparent and 0 is completely opaque. Looking at the entire sample here is a good way to get started in conducting the particle queries. Here, for example, we see 3 areas of a high population density. A small size mode at a high transparency, callout 2 in the upper left, a considerably larger sized mode at the same high transparency, callout 3, and a similarly sized mode but at a much lower transparency, callout 4. The distributions are reported in number format here, but they can be reported in volume percent also, callout 5. When switched to the volume format, the lowest size mode made up less than 1% of the total volume of the sample, verifying a small but negligible mode of very fine abraded particles, actually of little concern. Summary data for both graphs are listed on the right side of the display. Here, the same distribution is plotted in volume percent format and shows that the small abraded particles mode makes up only a negligible portion of the sample. So we're interested mainly in the 2 different transparency modes isolated from each other in the y-axis graph on the right. The first application example, reflective glass beads, discussed next, will utilize a transparency difference to isolate and identify 2 different components in the sample. We've been showing a measurement of a sample of glass beads used in reflective coatings for highway striping and signage, and we'll go into considerable detail to show how our image analysis technology can identify and quantify all the different components of the sample in one analysis. These beads need high sphericity and transparency to provide the highest reflectivity. But they also contain portions of braided and fused beads which are undesirable components and should be minimized during production. When used in highway striping, they also typically contain an added portion of sand to improve traction during wet conditions. This sand component also can be quantified. Pictured here is a very small section of the video file from the measurement of this sample. Any stored video file can be remeasured under different standard operating procedures, or SOPs, applying different sets of filters or classifications, which will be discussed later. From the top down, we see images of sand particles, fused beads, and good beads. The good beads are both spherical and transparent. This shows the display where all the pertinent particle queries for this sample can be programmed into one SOP. which can then be chosen to automatically apply all the queries to isolate the various defined components in the sample. In all, up to 7 different queries can be set up here, more than would probably ever be needed. Here we've set up 4 different queries in columns F2 through F5 to isolate 4 classes: transparent particles, bad beads, good beads, and sand. Transparent particles will include both bad beads and good beads. Then those 2 classes can be separated by applying an aspect ratio and curvature parameter query to that class. The sand ends up as the opaque or low transparency class. The curvature parameter used to help isolate transparent spheres is unique to Microtrac. Here are segments of the image files for the three of the components in the glass bead sample. Good beads are on the left, based on low aspect ratio and high curvature. Bad beads are on the right, based on transparency and low aspect ratio and curvature. And sand, based on lowest transparency. Consultation with Microtrac technical personnel can assist customers in setting up the appropriate automatic queries in the SOP. This is the XY distribution graph and table display. The graph is plotting cumulative percent finer distributions in volume percent format. Going from top to bottom, it's showing the total sample result, 100% of the sample, followed below by the various components of the total expressed as percent of total by volume. We've calculated an intermediate class, transparent beads, which includes both good beads and bad beads, and that class makes up about 72% of the sample. The good beads class makes up 47%, the bad beads 35%, and the sand 18% of the sample by volume. And all of these components data were determined from one measurement of 84,000 particles in 4 minutes. All calculations take place in real time during the measurement. In our second example, stone aggregates used in construction of highways, runways, and dams need to have ratios of lengths, widths, and thicknesses measured and reported. This requires both 3D image analysis to get the third major dimension, thickness, and the ability to quantify different classes and components for their various ratio limits. Ratios like length over width, length over thickness, and width over thickness. Flat particles, elongated particles, and flat and elongated parameters for particles within each ASTM standard specified size fraction and for the entire sample are required for either superpave or non-superpave highway applications. This previous slide of reported parameters highlights in red the dimensional ratios which need to be calculated for the aggregates application to meet ASTM D4791 standards. Using sieve analysis and handheld gauges, this test currently takes hours to complete. Using the PartAn 3D, it can be finished in less than 10 minutes on a much larger, more representative sample of particles. Here's a view of a measurement result of flat, the ratio width divided by thickness, analysis displayed on the XY graph and table. Following the numbers around the graph, 1 is a cumulative percent finer plot of the actual sieve data size distribution. 2, the red curve, is the PartAn calculated sieve data. 3 is PartAn width, 4 is PartAn thickness, 5 is the 3:1 width to thickness ratio, and 6 is the 5:1 width to thickness ratio, both as a percentage of the total sample. Any ratio can be chosen and reported. Length over width, width over thickness, and length over thickness. On the table to the right, columns 4 and 5 display these two ratio percent by size fraction. Any ratio can be chosen, including the sometimes used 2:1 ratio. The laser melting process is one of the many new manufacturing processes now called additive manufacturing, aka 3D printing. Only dry, highly spherical atomized powders are used as feed material to this process, including metal and ceramic powders, glass, and plastics. The process uses a rotating mirror, which, by following a CAD pattern, directs a laser beam onto the top powder layer, melting the powder layer on top of the previous layer of the part. All particles not melted onto the part are scraped off while the next layer is loaded. Attempts are made to successfully reuse the unmelted particles for as many cycles as possible before they show too much wear to meet size and shape criteria. It can take 10 pounds of a metal powder to produce a 1-pound part if the left behind powder can't be recycled. Parts. Below is an example of the complexity of a part that can be made by laser melting. Parts can also be very durable, as they're made in one structural piece requiring no subassembly. They're also much more customizable on demand. One machine supplied with a number of different available CAD programs can be used to make individual custom parts, saving the large expensive tooling to produce a single part type when needed. Very small amounts of contaminants in the feed or off-spec material in the recycle stream can cause point defects that affect the integrity of the final part because of the extremely thin surfaces which can be formed in laser melting. Here's a list of size and shape parameters again. All parameters highlighted in red can be identifiers of contaminant particles in the feed of narrow spherical particles. dA, a size parameter, is the area equivalent diameter of the particle, which closely correlates to the equivalent spherical diameter reported in diffraction data. Circularity is a form parameter. On a scale of 0 to 1, 1 is a perfect circle. Circularity is affected by both surface roughness and aspect ratio. Note the particle image shown. Width over length aspect ratio on a scale of 0 to 1, 1 is a perfect sphere. Elliptical forms would be less than 1. Convexity is one of the surface roughness parameters. On a scale of 0 to 1, 1 is a perfectly smooth surface with no concave indentations. Transparency is a measure of the light intensity. A higher transparency indicates a more translucent particle. The blue outline of a particle image is an example of a particle with parameters which can indicate contaminants in a powder sample or out-of-spec particles in the recycle stream. An elongated, rough-surfaced, or translucent particle image can indicate a contaminant in a metal powder sample. The proportion of the sample identified as contaminants or off-spec particles can then be quantified and reported. Images can be captured and copied. Here are two different contaminant particles. The image on the right, when selected from the frame in the View Particles display, automatically lists all parameters for that particle to the right. The contaminant parameters listed below each image show low circularities, low aspect ratios, and low convexities. These parameters should all be close to 1 for a good, smooth, spherical particle. Image analysis technology is the only one that can provide this kind of information. To sum up, different components in a particulate sample can be isolated and quantified into subdistributions of that sample from only one PartAn measurement. These different component classifications might be particles that have morphological properties which either meet or fail quality specifications, or they could be contaminants from the process, handling, or packaging, which can be identified by meeting certain morphological criteria. Search criteria in the software can be used to determine parameter limits which identify the classes desired. These classifications can then be added to the SOP for automatic quantification and reporting. Well, that concludes our presentation for this morning. And Claudia, I'll turn it back over to you for some final comments and to take some questions and answer some questions.
Thank you, Terry. We got a few questions during the presentation, and you're still able to submit your questions on the questions pane in the attendee control panel. So our first question comes from Mark. He asked, does the PartAn 3D correlate well with the sieve analysis?
We have two different routines that can be used to develop a correlation between any of the PartAn size parameters and the actual sieve analysis data, and they can be developed to overlay each other almost precisely. And many people use these correlation routines.
Great, thank you. Our next attendee asks, what is the particle size range, the minimal particle size, that can be measured or analyzed?
The minimum size on the PartAn 3D is 35 microns. This is a dry analysis instrument. We have a wet analysis instrument that measures down to 0.5 or measures down to 5 microns, and we have an ultrafine dry system that measures down to 5 microns as well. But these two instruments only report 2D analysis, like all of the other image analyzers on the market.
Okay, and what is the minimum particle feature size that can be measured?
That would be about 10 microns on the lower size limit of 5 microns and about 50 microns on the PartAn 3D.
Great, thank you. So someone else is asking, how many particles can be analyzed in 10 minutes?
It depends on the concentration of the sample. You can feed the material at various rates, and it certainly depends on the size distribution of the particles. We've measured some fine samples into the millions in less than 5 minutes.
Great. Okay, so we went over the minimum particle size. Now, what is the largest size particle that can be analyzed?
For the instrument we just discussed, it's 35 millimeters. And we have a PartAn Maxi that goes up to approximately twice that size. So there are other models, and the Maxi model is also a 3D analyzer.
Okay, Terry, is the customer able to specify the recording time?
You can set up the instrument to measure for a certain number of minutes, user selectable, or you can set it up to start a measurement when it first sees particles tumbling through the sensing zone, and then you can set up area limits to end the analysis. In other words, when the sample flow becomes so low that you're only seeing maybe one particle every few seconds, it can end the analysis at that point. So you have a couple of different ways to set the timing.
Okay, and Larry wanted to know, is there an option for wet measurement?
Yes, as I mentioned, there's a wet system that goes down to 5 microns, and the upper end of that is approximately 2,000.
Great. So Steve also would like to know, is the procedure accepted in ASTM D4791?
It's in the process of being evaluated by several of the DOTs for measuring aggregates, and so we're working towards that end, and they're using one of our instruments for a complementary cooperative study. So we're aiming in that direction.
Awesome. Okay, so is there any difference between organic and inorganic particles for analysis, even surface treated ones?
No, the instrument would not distinguish between organic or inorganic particles. It sees any particle as an image that has some degree of gray light intensity, anywhere from very translucent up to completely opaque.
Okay, and Roland would like to know, how is the volume of an individual particle determined?
In the 3D analysis, we measure all three major axes, length, width, and thickness, and we actually calculate that volume as the product of those three dimensions. So it's the most accurate volume analysis that a particle characterization system can provide.
Great, thank you. So Robert is asking, how does the PartAn 3D keep the particles separate and not clumped together during measurement? Does it use a fluidized bed or another method?
The flow of the particles on the vibrator can be selected by the user, and the shaking on the vibrator deagglomerates most powders. You could use, if you have some very tightly fused powders, which you really only get in the very fine powder distributions, which we have the fine dry powder system for. That applies vacuum and high pressure air to deagglomerate the material just before it enters the sensing zone.
Great, okay, and we have two more questions. One from Mike, is the data easily extracted to Excel?
It's extremely easily extracted to Excel. If you copy the image file that shows all the parameters for all the particles, it goes right into an Excel spreadsheet.
Great. Okay, so actually the last question is two parts. Can suspensions be analyzed or only dry samples? Can your instrument for wet samples give concentrations?
We have parameters that correlate with concentration, and the answer is yes. We have a wet system, and we have routines that correlate with concentration. So if you know the concentration of a material, you can run a few different concentrations and correlate that number to your concentration.
Okay, well, that wraps up our questions. If anyone has any further questions, they can feel free to submit the question through our website or email one of us directly. So thank you all for attending today's webinar. As a thank you for joining us today, we're offering a complimentary lab analysis of your sample, whether it's imaging, laser diffraction, or dynamic light scattering. Simply visit our website, or you can contact our laboratory manager directly, Tony Weigel. And if you want to replay this presentation, you'll be able to find it on microtrac.com. Thanks again for joining us, and we'll see you next time.
Claudia, I just wanted to add my email address down here in case they have some questions that come up later. They can get in touch with me directly.
Okay, that's great. Thanks everybody.